to lecture 4 in this series of introduction to proof videos. Today we're going to be covering section 1.4 in JIAM, the General Introduction to the Art of Mathematics, and there's a lot of content here. Although this stuff is all going to be more or less just introduced and not dealt with in a great deal of detail. But the idea is that we'll get a smattering of different definitions from elementary number theory that we can use in our early attempts at doing proofs. So we've already talked about even and odd a bit, but there's also going to be decimal and base n notation, the divisibility symbols. That's a pretty nice area for doing some proofs. Floor and ceiling, which are basically ways to talk about rounding. Div and mod are pieces of the quotient and remainder theorem, and binomial coefficients. Well, those are the topics. Let's get rolling. The first one, even and odd. Of course, we've talked about even and odd actually a few times before, but now we're ready, mostly because we have the concepts of quantifiers around. We're ready to give more or less standard and precise definitions for these things. So first I'm going to say it in words. An integer n is even exactly when there's an integer m such that n is 2m. N is 2m. The notation is only different in that certain of the word phrases have been replaced with symbols. So you read this, as you're reading across this stuff, it is said exactly the same way. An integer n is even exactly when there exists m in the integers such that n is equal to 2m. What are the changes? The phrase exactly when has been replaced with this double-headed arrow thing. And the there is, that's become this there is sign, the existential quantifier. I think I mentioned that in this bullet here. Yeah, exactly when became the two-headed arrow. There is turned into that. What happened to such that? That was a part of the verbal thing. We just don't have a symbol for it. In fact, there is a symbol for it that some people use, but I prefer not. I feel like you can just drop it and it makes perfect sense. There exists the m so that n is equal to 2m. Odd looks rather the same. In words, you'd say an integer n is odd exactly when there's an integer m such that n equals 2m plus 1. I know we had 2m minus 1 and some other options in the activity, but 2m plus 1 will do great, and here it is in more or less pure symbolic form. We're defining the concept of oddness, so the if and only if, I just used the phrase I didn't mean to use. Well, you're going to find out soon enough this double-headed arrow is also known as a biconditional, and people pronounce it if and only if. It means the same thing as exactly when. Two things are true at the same times. Anyway, there exists an m in z such that n is equal to 2m plus 1. All right, so we'll certainly be able to do some, I don't want to be derogatory, but a lot of people call these baby proofs because they're pretty easy. But we'll definitely do some baby proofs using the even and odd concepts. Decimal and base n notation, that's our next stop. Base 10 is something you're so used to. It's rather like the thing about, are fish aware of water? You probably are so familiar with it that you've stopped noticing it. So let's back away a little bit and notice it. When you write down a number, and just as an example, I'm picked the number 147 here, you're using place notation. You're using the idea that the sevens in the ones place, but the ones in the hundreds place, right? They mean different things. Place notation lets us write arbitrarily large numbers using just the 10 symbols, 0 through 9. This is a pretty major advance. I also teach a history course and had to learn how the Egyptians do it. Their biggest digit, as it were, is a picture of a guy going, like he's really surprised. I think he's supposed to be a scribe that's like losing it because he's being asked to deal with a huge number, and that number is 1,000,000. The biggest number they could write down was 1,000,000, or I guess they could write down a couple of those dudes, and then they'd get, a couple of million. But numbers in the billions or the trillions, like our national debt is, were just incomprehensible to them. And face it, as math people, got to recognize that in the scope from 0 to infinity, a couple of trillion is really close to the zero end. Infinity is way out there, right? Anyway, when you write 147, it really means this: 1 times 100 plus 4 times 10 plus 7. The ones in the hundred place, the fours in the tens place, the sevens in the units place. I sometimes like to write this out with uh, the, the places really written using exponents. So that's the 10 squareds place where the 1 is. The 10 to the 1 place is where the 4 is, and the 10 to the 0 place, because anything to the 0 power is 1. That's the units place. Now, think about this. Powers of 10 in that's because of these things, right? We started out counting on our fingers, and we've been stuck that way. People could very reasonably have used base 5 instead of base 10. And, you know, if you're not wearing shoes, base 20 makes sense. And people really did invent numbers long before they invented shoes. So, you know, it's possible we could have done base 20. 20 is a little tough because it requires school kids to memorize the names of 20 different things that would be the one digit numbers. And that might be asking a little bit much. I'll just point out, again, this little history nugget that's sort of fun to know about. In ancient Babylon, they used base 60 for their numbers. The truth of the matter is they had a way to write numbers that was more or less base 10, but they only wrote them up from 0 up to 59, and then they used these groups of base 10 numbers that went 0 to 59 to write base 60 numbers. And base 60 is still floating around today. We see it in the 60 minutes in an hour, 60 seconds in a minute. The way we do angles also goes back to Babylonians, and the Babylonians used 6 60s to make a full circle. But I even think it's amusing to point out there's a unit in astronomy known as a parsec. It stands for parallax second, and it's the distance an astronomical object would be away from the Earth if its parallax shift, which you should look that up if you're interested. But if a certain parallax shift was 1 second of arc, so this very high-tech, spacey sounding unit, the parsec, which they famously got wrong in the first Star Wars movie, actually goes back to ancient Babylon because it references seconds of arc. That's kind of messed up and funny and, I don't know, cognitively dissonant. Okay, so let's try base 5, because why not? We've got 5 fingers. Let's see if I can do it. I'm hoping, from your perspective, these are the ones place and these are the tens place. If not, this will be messed up. But you start out with 0, no digits up, and then you begin counting. Am I counting right? 1, 2, 3, 4. And when I hit 5, I say, no. Put those away. Put one up on this side. Right? So that this, which is a 1 and a 0, I guess we could say 10, but it's not really 10, it's 5, because we're in base 5. And then we would have 11. That's really 6, 7, 8, 9. A whole handful? No. Put a second one of these hands up. And we're right now at the actual number 10, although if we were talking about base 5, we would probably call it 20 or 20. I think I don't want to say 20 because that's what we all know for the name of a base 10 thing that's a little bit bigger than we are now. But 2e maybe would make sense. All right, then 2e1, 2e2, 2e3, 2e4, 3. 3e1, 3e2, 3e3, 3e4, 4e. 4e1, 4e2, 4e3, 4e4, 5e. And now we should put this away and get somebody else to put up another finger. We'd need a friend to hold up a finger, because we're at 100 in base 5, which would really be 5 to the second power. That would be 5 squared, or 25. But that's isn't that interesting? You can count on your fingers up, and you've got 10 fingers, but by using 2 groups of 5 and place notation, you can count all the way to 24. You can do even better than that, but we'll come back to that in a second. I do want to give a shout out to the Schoolhouse Rock people that made these educational videos back when I was a child, and you can still find them on no doubt on YouTube. Look up Little 12 Toes. It shows, I think it's more or less aimed at a second or third grader, but it shows a kid how to do base 12 arithmetic. If we're in an arbitrary base, then I'm using these x's with subscripts on them for the digits of a number. So I have, I guess that's actually n plus 1 digits. They're numbered 0 through n. But what that means is, well, each place, the subscript value 0, 1, 2, up through n, those correspond to the power on the exponent, the exponent on the base, rather. So the units place is the x0 times b to the 0. The basis place is x1 times b to the 1. And the last place we have here is xn, b to the n. I've put dots in there because I hope it's pretty clear what the pattern is. X of whatever times b to the same whatever. Though if you're doing one of these funky bases, usually it's a good idea to warn people, right? Because people normally think you're writing base 10. So if you're going to be using a different base, unless it's clear throughout a whole chapter of something that you're in a funny base, put a subscript on it to indicate the base. So this is 1, 2, 3, 4, 5 in base 7. And there it is what the place notation means. 1 times 7 to the 4th, 2 times 7 cubed, 3 times 7 squared, 4 times 7 plus 5. I just plug that into a calculator, and that's what it is in base 10, 3267. In base B, notice that the digits run from 0 to b minus 1, much like when I was holding up my fingers to do base 5. I stopped really when I had 4 fingers up. I never put 5 fingers up because that meant go to the other hand and put a digit up. So just like we're in base 10, but the digits end with 9. It is useful, really, when you're in one of these unusual bases to remind yourself what number is going to act like 9. The number that acts like 9 is the one that tells you, when you reach a 9, it's time to think about bumping up the next place as you go counting through numbers. Anyway, yeah, the base itself is written as a 1-0, 1-0 sub b, if you're using my advice of putting a b subscript on things. There's a couple of bases, really 3, that show up in computer science. Binary is well known. Everybody knows, I think, that computers run on binary because really transistors that are how computers actually do their calculations can either be energized or not. And they're either on or off. And so those two states of off and on become the digits 0 and 1. And that's what the digits are in binary, just zeros and ones. Octal is, maybe the word octal sounds to you like octagon, or are there other words that start with OCT like that? Anyway, octal means base 8. So the digits are 0 through 7. And hexadecimal, which if you think about it right, hexa is 6 and deci is 10, and so that's 16, base 16. There your digits are everything from 0 through 9, and then additionally we'll use the letters A through F as the digits. I'm going to take a side tour to talk about binary and the digits, the way to count on your hand in binary. I'm trying to hold, so let's resize this camera window so you can see this more clearly. Not my face, but my hand. I've written the powers of 2 on my hand. That was actually hard to do, I got to admit, because I had to write with my left hand on my right hand, and see that 2 is off on the side a little bit. So 1 is on my thumb, 2 is on my forefinger, 4 is on my index finger, 8, and then 16 on the pinky. I'm intentionally holding my hand faced away from you because this is where the numbers are written, but also because 4 gets rude when we get to it. Anyway, the way you count in binary is to emulate the digits. The digits are only zeros and ones, so either hold the thing down or pocket up. That's 0, that's 1. This is 2, that's 0 again. Right? So that would be 4, and that's why I'm holding my finger faced away from you. So yeah, here's 1, here's 2, that's 3, 2 and 1, right? When I've got 2 digits up, I bring them down and bring the next one up. The number after 3 was 4, then 5, 6, 7. Now this in binary, 1 is the thing that acts like 9, right? So 1 is really this is as if I had 999 up, right? And what comes up after 999? 1,000, except it's only 2 to the third, not 10 to the third. So we get 8. This is possibly the hardest one to hold up because that finger just doesn't want to go by itself. There's 9, there's 10, 11, 12, 13, 14, 15, 16. Did you see how I went from 4 digits up, 9999, to 1000? Well, 1 and a lot of zeros. So after 16, we'll see 17, 18, 19, 20, 21, 22, 23. I'm sorry, I'm moving myself off screen. That's 23, right? So then those coming down and that one up, that should be 24. Yeah, 16 and 8, 25, 26, 27, 28, 29, 30, 31. So you make it to 31, the sum of 1, 2, 4, 8, and 16, all in one hand. If you bring up your other hand and scroll on that with the other powers of 2, you can go to 1,023 on 10 digits. So computers, it may sound like ones and zeros is very limiting, but actually ones and zeros gives you a dense way to encode the numbers. Right, so let me take a second and put this back to small size so we don't have to stare at. It's hard to get the handle for where it changes size. Close enough, I think. And let's continue with the slides. Conversions, right? So if you're in some funky base and you need to go to decimal, that's easy. Just use the place value meaning, the meaning of place value. So just quick example of it, if I have 1, 2, 3 and it's in base 5, what that means is 1 times 5 squared plus 2 times 5 plus 3. And you just plug that in your calculator, you get 38 out, right? That's all that stuff in the way I've written it here, that's all base 10 numbers, or may be treated that way anyhow. To go from decimal to another base, you can use a thing called the repeated division algorithm. We will look at the repeated division algorithm in the homework problems and in the worksheet for this lecture. But the big thing to watch out for, you do what it kind of sounds like. You keep repeatedly dividing by the base. And you get digits. The digits are actually the remainders that pop up as you divide things by the base. The problem is the digits come up in reverse. That's the most common mistake, is people forget that they're getting the digits in backwards order. So watch for that. Okay. For the bases common in computer science, you can use binary as what is known as a lingua franca, a language of trade, or a language that everybody kind of knows. Like today, I think English has become a lingua franca because pretty much wherever you go in the world, people know a little bit of English at least, so you can communicate to an extent if you know English. There is a table on page 33, which I'm going to complete for us here because it shows you how to use, this is the table, or tables really, that I'm referring to, how to use this binary as a translation aid between other between the various computer science bases. So this table has the octal number. Well, let's point them out. We've got the octal digits 0 through 7 in the small table, and it turns out each octal digit can be thought of as a binary triple. So all I have to do is sort of count upward to fill out this table to get the binary digits here. After 001 is 002. No, it isn't. I'm messing with you. 010 is the binary version. I think I'm going to need to switch pens because this blue one is dying. 010, and then 011, then 100. Right? When that number I just wrote, 011, just like 99, the thing after it is 100. Then because we have zeros after the or in the early places, we get to begin counting over again. So just bump up the units place, 101, then 110, then 111. Now the thing after 111 would be 1000, but that's not needed for octal. We just need binary triples for the first 7 digits. So 0 and the 7 non-zero digits. Got it? Okay, so we can pull the same thing in hexadecimal. Uh, hexadecimal, let's see. After 01010, we'd have 0011, then 0100, then 0101. I'm just going to stop talking and fill them in, okay? No, I messed up. I could tell I messed up because I have a checkpoint. That's, sorry, I'm just going to cross it out and do it. That should have been 0111, and this one should have been 1000. Then 9 is 8 plus 1. A is 1010. And actually, I'll point out that A is another good checkpoint. A is actually equal to the decimal number 10. If you're 10 in base 10, the ordinary number 10 is A. And its binary representation has two 10s in it, 1010, right? So that's kind of a nice point to remember. A is 1010. B then is 1011 or 1011. And F is 1111, finally. So if you have a binary number, you can convert it to any of these. That's easy, just by looking up the groups of binary symbols correspond to single either hex or octal. It takes 4 binaries to make a hexadecimal number. It takes only 3 binary digits to make an octal number. But suppose I had something like this, 757 in base 8. I can tell you what that is in binary real quick. It's 111. That's what 7s are. 5 is 101, right? And then 7 again, 111. So there it is in base 2. And all I have to do to think of that in hexadecimal is break it up into groups of size 4 and look them up. Now this initial, or this leftmost 1, you got to watch out. That should be thought of as 3 zeros and then a 1. You need to, what they call, pad it with zeros to find something, but that's a 1. What is 1110? That's over here. It's an E. And 1111 is F. So there is a representation of that number as a base 16 thing. 757 in base 8 becomes 1EF in base 16, and it's that horrible thing in binary. Well, that was fun. Let's go back to our normal setup. I'm going to need the calculator eventually today, so it's still sitting there. Divisibility, what does that look like? There's this very succinct notation for the situation where one number divides evenly into another. Oh, the title of this slide is gazinta. I got to tell you this anecdote. When I was a junior high school student, they had a sort of an experimental program to see if kids could learn abstract math at that age, and it didn't go that great. But the teacher had a kind of distinct Maryland accent, and when he talked about one number dividing another one, he kept saying gazinta, like 6 gazinta 18. And a lot of us had a hard time figuring out what it was meant, but it was goes into, right? He was saying gazinta, but it was divides. The better way to say it is just divides. So the way you do this is you just put a vertical bar between the two things. 7 vertical bar 42 means 7 divides 42. Or to be more, put more detail on it, there is no remainder if you try to divide 7 into 42. Notice how the order of the numbers is flipped around, as well as the vertical bar turns into a slash or a backslash, the fraction sign when you compare actual division to the divisibility question. So my point here is that the vertical bar is a question. It's asking, does this thing gazinta this other thing? So 7 divides 42 is true. It's not a number, it's true. 42 over 7, that's 6. Similarly, here's a couple of false ones. 5 divides 37? No, it doesn't. You'd get a remainder if you divided 5 into 37. So that's false. And 37 over 5, you have to switch the order around as well as change the symbol. That's 7.4. So another way to think of this is the division symbol, the divisibility symbol is true precisely when the actual division ends in a 0.0. You have no decimal point or no remainder. It's kind of cool that the actual definition we use for the divisibility symbol completely avoids doing division. You don't have to do division at all. Here it is. D divides n exactly when there is a k in z, that is, there is an integer, such that n equals k times d. So you see, k is the thing you would get as the quotient, but by writing it this way, we've avoided division and just done it in terms of multiplication. You're saying the one thing divides the other if you can find the quotient and it's an integer. Yeah, but expressing that existence of the quotient in terms of the related product. So pop quiz here now. Let's see if you guys can do this. I'm not going to say it for a second. See if you guess it before I give away the answer. What is the number k that must exist to show that 7 divides 91 is true? Okay, I guess that was long enough. 91 often fools people because it seems like maybe it ought to be prime, but it's not. It's a multiple of 7. You can probably spot this because 91 is 21 bigger than 70. 70 is clearly a multiple of 7, and 21 is a multiple of 7. You put two multiples of 7 together, yeah, 91 should be. Well, I guess that means it's 13. 13 times 7. I'm not trusting my mental arithmetic. Yep, 91. So 13 is the k that tells you that 7 divides 91 is true. Okay, next we're going to look quickly at floor and ceiling. This will do really quite quickly because they're easy ideas. You just need to see what the notation looks like. It looks like that. It looks a lot like an absolute value symbol, except there's this extra bar at the top. So pi with that ceiling, they call that the ceiling notation, means round pi up, and so you get 4. The basic idea to use ceiling notation wherever you would round up, wherever it makes sense to round up. There are certain areas where it's important to round up and certain times when it's important to round down. I give an example in the book of a bunch of people getting on an elevator, and the elevator has a sign that says, maximum load 1,300 pounds, but everybody weighs 200 pounds, so how many people can go on? Well, you better not go to 7 people. You'll get over the maximum. Maybe it's okay if there's a safety factor, but if you're worried, if it looks rickety, then don't go with 6, round down. The idea is to take 1,300 divided by the weight of the people, which is 200. 1,300 over 200 is 6.5. Should we go to 7 or stick with 6? In the case of something that has a safety factor, round down. Rounding up also is appropriate in other circumstances. I'll let you think about that a sec. Here's the formal definition. For all x in the reals, y is equal to the ceiling of x exactly when, 2 bits here, y is an integer, and this compound inequality. How do we read that? Well, look at the the right part of it first. X is less than or equal to y. That's part of it. The other part of it is that x is bigger than y minus 1. But again, notice one of these is a less than or equal, and the other is a less than. I usually look at a compound inequality like that and say, x is between y and y minus 1. But then I examine the endpoint and notice, well, wait a minute, it could be equal to y, but it's got to be bigger than y minus 1. So when you're rounding a number that's already a whole number, you don't have to round. You leave it alone. That's what that's saying, whether you're rounding up or rounding down. That's the case. Translation. Oh, I just did the translation. I was saying I needed to, that was a bullet on the slide reminding me to translate for you. The floor notation is similar here, except the little tick marks or whatever are at the bottom of the absolute value sign. So pi rounded down is 3. Here's the formal definition. It looks exactly the same, except when we get to that compound inequality. Oh, and I've typed it wrong. There is a typo here. That should be a less than, not a less than or equal. I'll fix that in the slides before I put them up as the handout slides, but we'll just in your mind turn that into a less than right now. Yeah, so x lies between y and the number 1 bigger than y, but it may be equal to y. It must be smaller than y plus 1. That's how you know you're rounded down. So, okay, div and mod. These are just names that people use for the quotient and remainder when you're doing division. I just want to quickly remind you of something that's pretty old. You did division a lot back in 3rd grade or something. Suppose I had the number 17 and I was dividing it by 5. It's that setup, right? Where you have the L-shaped bar. The one number is under the bar, the other number is out front. This is the D, and that's the N. The D is going into the N. 5 goes into 17 3 times. 3 times 5 is 15. We subtract and we get 2 here. And we stop when we're at this point because why? 2 is smaller than 5. If I had a bigger example, we might have to keep going until we got to something that was smaller than the divisor. But we're done here because 2 is in the range between 5 and 0. So that number is called the remainder, and this number is called the quotient. Right, so if you're doing that, you may also want to see how that plays out on a calculator. There's a fairly easy way to figure out quotient and remainder when you're on a calculator. Suppose, let me do the same problem, which is 17 divided by 5. I get a decimal number, 3.4. 3 is the quotient. So if you take away the quotient from that decimal number, what you've got is kind of a slightly hidden version of the remainder. The problem is that that's the remainder over the divisor. So just times it by the divisor. We were dividing by 5 in this one. Oh, I don't want to divide, sorry. I want to times by 5 to undo the fact that that 4 is divided by. So 3 is visible in the actual answer, and the decimal part, 0.4, if you times it by the divisor, it gives you the remainder part. Cool. So yeah, suppose in general we've got n being divided by d. The results are a quotient q and a remainder r. The names for those are n mod d, and there's another typo. I should have proofread these slides before I got that. I'll fix this on the handout version, but where it says n division sign d, the old school division sign d, it was supposed to say the word div. So n div d written out like that. Oops, I'm so low there. N div d, that's your quotient. And n mod d, that's your remainder. But quick example, 17 mod 5. Think about that's funny, that's the example I just did. Totally random chance that I did that. So 17 mod 5 is 2 because that's the remainder. 37 mod 6 is 1 because if you spot that 36 is just 1 smaller than 37. So 6 would go evenly into 36. The number 1 higher would give you a remainder of 1. This is interesting to note that the mod operator being 0, that's equivalent to saying that the d actually divides evenly into the n. So if n mod d is 0, same thing as d divides n. This is another example of a place where we could have equivalent definitions. That, of course, we'd need to prove that equivalence. I'm just saying it for you here. Notice that I haven't given you examples of div It's because div is actually used very seldom. I mean, you can put it in there if you like, but like 17 div 5 would be what, 3 that we got before. 37 div 6 would be 6. But we don't see them very often, so I'm skipping that. All right, binomial coefficients. Last thing in this section. Sorry for this being like such a grab bag of different things, but I think these will all be useful to us in the near future. Have you seen Pascal's triangle before? I hope you have. This is a well-known arithmetical triangle that helps you calculate things. It's useful if you need to expand powers of a binomial. Like a typical example would be if I want x plus y to the fourth power, I can just write it down because I go looking at this Pascal's triangle thing and I identify the row that's, oh, I can't highlight in here. The one that has the 1, 4, 6, 4, 1 in it. Those turn out to be the coefficients in my expansion of x plus y to the fourth. And the powers on the various things just start out with everything on the x, so x to the fourth. Well, okay, there's a coefficient of 1 in front of that. Coefficients, I said, were the numbers out of the fourth row of the triangle. So 4 is next. Then it's got x cubed y. Then it's got, I'm trying to, 6x squared y squared. Oh, I'm running out of space, so let me just break the line. 4x y cubed and ending with 1 times y to the fourth. That is impressive as hell if you know the trick and you can write down the fourth power of something like x plus y without even thinking about it. Just going, there's a triangle, 1, 4, 6, 4, 1, and the power on x descends, 4, 3, 2, 1, 0, and the power on y ascends. There's no y's, that's the 0th power. 1y, 2y's, 3y's, 4y's. Yeah, go impress your friends or roommates or whatever with that. If you have seen Pascal's triangle before, you'll know the trick is that you just put this boundary of ones on it, and then inside the triangle, a number is just the sum of the two things above it on either side. Like this, there's a 6 right there. It's the sum of that 3 and that 3. Or that 15, that's the sum of this 5 and this 10. 20, that's the two 10s, right? So it's really pretty quick and easy to create Pascal's triangle down to row 6. But for a lot of problems, you want to create Pascal's triangle down to row 52 or something. So that would maybe be a daunting task. Let me point out a couple of things. People, and me in particular, we're going to talk about the columns and the rows of Pascal's triangle. And they're numbered at 0, but B, the columns are really not columns, right? They're off at a big angle. And that's, honestly, that's just tradition. We could have squared everything up and had Pascal's triangle have a first column with all ones in it. People just always prefer the symmetrical look of it with the triangle, the equilateral triangle versus a 90-degree triangle. But the entry in, if you understand that column K represents the kth of one of those diagonals, the entry in row N and column K is written in this slightly funny looking way. It looks a little bit like somebody forgot to put a fraction bar in. Please don't put a fraction bar in, because that would mean something else entirely. And this is not meant to be a fraction. It's a way of referring to the NK position in the triangle. That symbol with the N over the K in parentheses is pronounced N choose K. And what it does is counts the total number of ways you could pick K things from a set of size N. So for instance, I'll give you an example of an important binomial coefficient. If you play poker, 52 choose 5, that is the total number of ways you could pick a hand of size 5 out of a deck with 52 things in it. And so that's the denominator you use for all the odd computations in a game of poker. Okay, so fortunately there's a formula. We don't have to write out uh, 52 rows of Pascal's triangle to find out what this number is. But we do need to know about factorials before we can do that. I suspect many of you will know this, but in case you don't, you write an exclamation point after a number to mean the factorial of it. And the value of n factorial, some people, particularly in computer science world, they'll read that exclamation point as bang. So they'd say n bang. In math circles, people are more likely to say n factorial. I kind of advocate for saying n bang because it's quicker, but whatever. The value of n bang is the product of everything from n all the way down to 1. People usually think of it as a descending product. So here's an example. 7 bang is 7 times 6 times 5 times 4 times 3 times 2 times 1. 5,040, if you want to work that out. There is one thing I forgot to put a thing in the slides about this, but it's worth noticing that we have a little bit of a conundrum when we think about 0 bang. What does it mean to multiply all the numbers from 0 down to 1? Well, 0 is already below 1, so that actually means a product that has no terms in it. And while you might like to think 0 bang should be 0, there's good reason to think that a product that has no members in it should be treated as 1 instead. And so that's actually just defined that way. 0 factorial is 1. I think there's quite reasonable ways to see that should be that way, but again, that's something we'll speak to later. So in terms of factorials, n choose k it's got n factorial in the top, it's got k factorial in the bottom, but also in the bottom it has the difference between the two numbers factorialized. So if I want to do this example we have here from poker, 52 choose 5, that would be 52 factorial upstairs, 5 factorial in the bottom, and also, what is that difference? 52 minus 5. Is that 47? Now, I honestly can't stand to leave this without mentioning one other thing. 47 factorial and 52 factorial have a lot of the same junk in them, right? Everything from 47 on down. So if you canceled all the things from 47 factorial out of the 52 factorial, what would be left is 52, 51, 50, 49, and 48. Am I off the screen? Sorry about that. And my handwriting sucks. Anyway, this is the descending product from 52 down to 48 over 5 factorial. That happens to be 120. You can actually also find things to cancel out of this factorial and these numbers, but let's leave that be for now. Oh, or you can use a calculator. Yeah, let's point out a couple of things about the calculator. There are things in the math submenu on the TI calculators that calculate both factorials and these binomial coefficients. The factorial, let's do that first. You go into the math menu, and these things are all under the 4th heading, PRB, for probability. Whoops, I went too far. Do you see the exclamation point in position 4? I don't know what my last answer is, so that's probably a bad idea. How about if we put like a 5 in there? 5 bang, 120, like I claimed a second ago. If you want to choose one of the choose numbers, what you have to do is, let's put in 52, then go back to the math menu, go to the probability section, and see the one that's called NCR. C stands for choice here. They use N and R. Math people almost always use N and K for some reason, but NCR 52 choose 5 would be input in the calculator like so. It's 2.6 million, more or less. So there's a lot of different ways to get a poker hand. We could do that. There are similar commands for that in CoCalc, but I think this video has already gone a bit long, so let's call it quits right here. Thanks for watching. See you soon. Bye.